Welcome back. This is section 6.3, trigonometric functions of angles. So what we're going to look at in this section is, what if we have angles that are larger than the 30 degree, 60 degree, and 45 degree angles that we looked at in the previous section? How do we find those trig functions, those trig values of angles that are larger than that? So what we're going to start with here is we're always going to want to consider putting our triangles, our angles, in standard position within the coordinate plane. So remember, standard position means that we're putting that initial side along the positive x-axis. And in this case, as long as our angle is positive, we're going to measure in that counterclockwise direction. So if you see here, what we've basically done is taken a triangle that we're familiar with the opposite, the adjacent, and the hypotenuse sides listed. We've put it into that standard position so that now the opposite side is the y value in your coordinate plane. The adjacent side is like the x value in your coordinate plane. And then the hypotenuse becomes that r value, which is like a radius of a circle. And you'll see that later as we start to look more at how this is all related, why we call that an r value. Okay, so in this case, the sine of theta would normally be opposite over hypotenuse. So in this case, the opposite is the y, the hypotenuse is the r, so it's y over r. Cosine would normally be adjacent over hypotenuse, so that's going to be x over r in this case. And then finally, tangent of theta would be opposite over adjacent, so in this case, that's y over x. So nothing has changed here. We're just calling these sides x, y, and r instead of opposite, adjacent, and hypotenuse. And again, the other three trig functions are just the reciprocals of the first three. Okay, so all you have to do is flip those. And again, we can't have 0 in the denominator, so that's why they're telling you here that y can't be 0 for cosecant, x can't be 0 for secant, and then our y can't be 0 again for cotangent. Now, once we start putting these angles in other quadrants other than quadrant 1, we're going to start having different signs in terms of positives and negatives for those trig functions. So in the first quadrant, everything's going to be positive. Our x value is positive, our y value is positive, the r value is always going to be positive, so all of our trig functions should be positive. Once we move over to the second quadrant, though, only sine and cosecant are going to be positive. All of your other trig functions are going to have negative values. Once we hit the third quadrant, remember the x and y would both be negative there, so that makes tangent and cotangent positive. All of your other trig functions are going to become negative. And then finally, in the fourth quadrant, cosine and secant should be positive. All of your other trig functions will have a negative value. And the way I remember this, if you set up a coordinate plane here, I'm going to say A, S, T, and C. And the acronym I remember here, I say all students take calculus. And so basically in quadrant 1, all of our trig functions are going to have a positive value. Once we hit the second quadrant, we have an S here, that's going to stand for sine. Okay, so our sine value is positive. And remember, cosecant is just the reciprocal of sine, therefore it's also going to have to be positive. Once we get to the third quadrant, now the t value or tangent is going to be positive, and again, its reciprocal is cotangent, so it also has to be positive. And then finally, in the fourth quadrant, we have C, which stands for cosine, and so cosine is positive in the fourth quadrant, along with its reciprocal of secant. So if you can just remember that all students take calculus, that's going to help you to remember first quadrant, everything's positive, second quadrant, sine and cosecant positive, third quadrant, tangent and cotangent positive, and fourth quadrant, cosine and secant positive. All right, so what we're asked to do in example 1 is find the cosine of 135 degrees. So first thing I'm going to do is I'm actually going to sketch this angle. So I'm going to draw my coordinate plane, because again, we want to put these in standard position. And so if I have my positive x-axis and I measure 135 degrees, we know that's bigger than 90 degrees. So we know we're going beyond this point right up here. We also know that it's smaller than 180 degrees, which would be halfway around our coordinate plane. So we're somewhere between 90 and 180. So I'm going to draw my line somewhere in the second quadrant, somewhere between 90 and 180 degrees. Now, in this case, what I actually want to do is I want to draw a new triangle, but I want to put it in the second quadrant. and you're always going to draw your triangle to the x-axis. Okay, so just be very careful here that when we draw our triangle, always draw your right angle back to the x-axis. So now what I've got to figure out is, well, what type of triangle do I have here? What is the angle within that triangle? So I know my initial angle that I'm starting from is 135 degrees. So from the positive x-axis around to that point, we're going 135 degrees. I need to find the angle inside of that triangle now so that I can set up my trig ratios. Well, to do that, I know if I go halfway around, it's 180 degrees. So if I just take 180 degrees and subtract that 135, that should leave me with the angle that's inside that triangle now. So that's exactly what I'm going to do. 180 minus 135. And so that actually gives us a 45-degree angle inside of that triangle. So we have a 45, 45, 90 right triangle, which is one of those familiar angles that we saw in our chart in the previous section. So now I should be able to find my trig ratios for that triangle. And so if you remember, cosine of 45 degrees from the chart in the previous section should be square root of 2 over 2. Now, that's not what we wanted to find. We wanted to find cosine of 135 degrees. But what I'm going to tell you is it should be exactly the same, because if I were to draw a 45-degree angle here, these points would actually be symmetric to each other. And so the values themselves should be the same. The only difference is now, because we put it in a different quadrant, it could have a different negative or positive sign to it. And so we have to keep in mind, in the second quadrant, cosine is going to have a negative value based off the slide that we just saw. And so now cosine of negative 135, or sorry, cosine of 135 should be negative square root of 2 over 2. So in general, we just want to sketch our angle. We want to figure out then what that new triangle looks like in whichever quadrant we've moved to. And then from there, we can figure out, is it going to be positive or negative based off of the chart that we just saw that tells us which trig functions are positive and negative in which quadrants. So the next one we want to do is tangent of 390. So again, I'm going to sketch this. Now, 390 is actually bigger than 360 degrees. So we know we're going more than a full revolution. We just need to figure out how much more. Well, 390 minus 360 only leaves us with 30 degrees. So we're only going 30 degrees more than a full revolution in this case. So that's going to leave me in this first quadrant right here. So again, we're going all the way around and back to here. Okay, but the triangle itself that we're going to look at is going to have a 30-degree angle down there. Again, I'm going to draw my triangle always back to the x-axis for my 90-degree angle there. And again, this is one of those special angles from our chart that we saw. And so what I want to find is, what is the tangent of 30 degrees? If we go back to our chart and look at tangent of 30 degrees, that should give us square root of 3 over 3. Again, we didn't want tangent of 30 degrees. We wanted tangent of 390. But in this case, 390 degrees is exactly the same location as 30 degrees. They're both in the first quadrant. And so we know that all of our trig functions are going to be positive there. So this actually remains positive square root of 3 over 3. So again, the steps for problems like this, you want to actually sketch out the angle, figure out which quadrant you're in, draw your triangle back to the x-axis, figure out if you're dealing with one of your special angles from the chart in the previous section, Think about what the trig function would be for that specific angle, and then make it positive or negative based off of which quadrant you're in. All right, now, reference angles. So we're going to let theta be an angle in standard position, again, from that positive x-axis. The reference angle, which we're going to call theta bar, is associated with theta, and it's the acute angle formed by the terminal side of theta and the x-axis. So, in other words, the things we just looked at in the previous slide are what we call reference angles. So back on this example, for 135 degrees, our reference angle was the 45-degree angle. So we're always measuring back to that x-axis, and so we got a 45-degree angle for our reference angle. For the 390-degree angle, once we subtracted, we got 30 degrees. 30 degrees was our reference angle, and so that's the one we're using to find the trig value. So again, always back to the x-axis. That's going to give us what the reference angle should be. All right, so example 2, we just want to find a reference angle for each of these theta values. So the first one we're given is 5 pi over 3. So first thing I want to do is I want to think about where is 5 pi over 3 located. Now, there's a couple of different ways we can do this. We could convert this into degrees, because in a lot of cases that's easier to kind of think about, especially for right now in terms of where these angles are located. You could also convert all of your degree measures on the axes, like 90 degrees, 180 degrees, and so on, into radians, and then try to figure out where 5 pi over 3 is based off of that. Now, in this case, I'm just going to go ahead and convert 5 pi over 3 into degrees. So remember, our conversion is we're going to multiply by 180 over pi. Now, if we do that, that should give us 300 degrees. So now what I want to do is think about where is 300 degrees actually located. So in this case, if I go 300 degrees, I know that's going to be somewhere less than 360, so less than a full revolution, but it's also bigger than this angle down here, which would be 270 degrees. So if you go 3/4 of the way around, that's 270. And so it's going to be somewhere in here, closer to the 270 than it is the 360. And so what I want to do now is draw my triangle back to the x-axis. There's your right angle. And my reference angle is always going to be the angle between the x-axis and that terminal side. Well, to figure out what that angle is, I know I'm going around 300 degrees to get to that terminal side. And so if I'm looking for my reference angle, theta bar, inside here, all I'm going to do is take the entire revolution of 360. I'm going to subtract that 300 degrees. And so I know there should be 60 degrees left over. So in this case, theta bar, or my reference angle, is 60 degrees. Now, because we were given radians to begin with, I probably want to go back into radians for this one. So I'm going to take the 60 degrees now, and I'm going to convert it back. So remember, to convert back, we're just going to multiply by pi over 180. So 60 over 180 gives us 1/3. So this gives us pi over 3 radians. So theta bar, or our reference angle, should be pi over 3 for this one. And again, as we go, you'll start to recognize where some of these radian measures are located without necessarily needing to convert to degrees. But for right now, if you need to do that conversion just to get a picture of where the angle is located, that's perfectly fine. Now the next one, we're going to go 870 degrees. Now, 870, definitely more than 360. It's more than a full revolution, right? So we know that. So what I want to do is think about, well, how many revolutions have I actually gone around? So I'm going to start subtracting off 360 degrees just to get a better idea of where this is located. So if we do 870 minus 360, that should give us 510 degrees. Still more than a full revolution, so I'm going to go again. 510 minus 360, and that should give us 150 degrees. Okay, so 150 is within a revolution, right? It's less than 360 degrees. So what this tells me now is I've gone 2 360s around, right? So I've gone around not once, but twice, and I have an additional 150 degrees beyond that. Okay, so I'm going 150 degrees, which again is going to be somewhere between 90 degrees and 180 degrees. Closer to the 180 than 90, so it's going to be somewhere out here. Okay, so all the way around to there, there's our 870 degrees. Now, what we're looking for is that reference angle, which again, always draw back to the x-axis. And I'm looking for theta bar, which is this angle inside the triangle right there. Now, rather than looking at 870, because we've already subtracted off the revolutions, I'm just going to think about the fact that we went 150 degrees around, and I'm just shy of 180. And so what I want to figure out now is, well, what's the difference between 180 degrees and 150 degrees? And that'll tell me what's left over for that reference angle. And so I'm going to do 180 minus 150. And so now I know my reference angle this time should be 30 degrees. Again, the whole purpose of finding these reference angles is because if they're the special ones from our chart, then we can actually find sine, cosine, tangent of those specific angles, and they should have the same values as these larger angles that we're looking at. Okay, again, we might have to change the signs, either positive or negative, depending on the quadrant, but at least we have a good idea of what those values are going to be from the chart. So this is basically the steps that we've been going through, just listed out now. Okay, so the first thing we want to do is find our reference angle. So find theta bar associated with our angle. From there, we're going to determine the sign of the trig functions based off of the quadrant, right? So again, in quadrant 1, everything's positive. Quadrant 2, sine and cosecant are going to be positive. Quadrant 3, tangent and cotangent are positive. And in quadrant 4, cosine and secant are going to be positive. Once we know that, then we can determine the value of the trig function for theta, right, based off of whatever theta bar is. Okay, so once we know the sign and we know our reference angle, then we can just figure out what the value of the trig function is. All right, so we want to find the sine, 240 degrees. So again, first step, let's go ahead and sketch this. Okay, so this time 240 degrees, bigger than 180, right? So I know it's bigger than 180 degrees. Remember, I told you 270 degrees is this angle right down here, and so we're somewhere between those two values. In this case, 240 is closer to 270 than it is 180, so I'm going to sketch my angle down here. So all the way around to there is my 240 degree angle. Now what we want to find is the reference angle first, right? Because from there, then we can figure out, well, what's the sign in that quadrant, right? And then we can figure out what the actual trig value is. Always draw your triangle back to the x-axis. So my reference angle this time is just this angle right here. from the terminal side back to the x-axis. Now this time, we've actually gone beyond the 180, right? So 240 was bigger than that. So to figure out how big that reference angle is, we're actually going to take our given angle, the 240, and we're going to subtract the 180, because that should leave us with that piece that's between the terminal side and the x-axis. Well, 240 minus 180 should give us 60 degrees. And so we know theta bar this time is 60 degrees. From there, we're looking at sine, right? So I'm going to find the sine of 60 degrees. And again, all we have to do is go back to that chart from the previous section. Sine at 60 degrees should give us square root of 3 over 2. But again, sine of 60 is not necessarily what we're looking for. We're looking for sine of 240 degrees. But we know, because 60 degrees is our reference angle, it should have the same value, except it could be negative instead of positive, right? So we have to think about which quadrant we're in now. Well, we're in quadrant 3. And in quadrant 3, only tangent and cotangent are positive, which means everything else should be negative, including the sine value. So that means we're going to get a negative square root of 3 over 2. So again, relating this to those steps we just saw in the previous slide, first thing we want to do, find that reference angle, right? So we sketch our initial angle, we find the reference angle. From there, we determine our quadrant. We're in quadrant 3, we're looking at sine, we know sine is going to be negative. And then from there, we can actually use our reference angle to find the sine value. Sine of 60 degrees is square root of 3 over 2. Because we're in the third quadrant, that makes it negative, and that's how we get negative square root of 3 over 2. All right, now part B, we want to find the cotangent of 495. So again, sketch your angle first. Now 495, bigger than 360, so we know we're going more than a full revolution in this case. So I'm going to subtract off that full revolution. So we're going to do 495 minus 360. It should give us 135 degrees. So I'm going all the way around 360 plus another 135, which again is between 90 and 180 degrees. It's right here, exactly halfway between them. So again, always draw your triangle to the x-axis. My reference angle this time is going to be this angle right here between the terminal side and the x-axis. Since I know that my additional piece, right, I don't want to go from the 495, I just want to use the 135 here. I'm going to do 180 minus 135, which should leave us with 45 degrees. So that is our theta bar this time. There's my reference angle. Now, once we have the reference angle, now we can think about our cotangent of that reference angle. So we do cotangent 45 degrees. And again, we can go to our chart to help us find that. Cotangent of 45 degrees should be 1. And then our last step is we actually want the cotangent of 495 degrees. And we just showed that that should be in quadrant 2. And so we just have to think about whether cotangent is going to be positive or negative there. Only sine and cosecant should be positive in that quadrant. So in this case, cotangent is going to be negative. And so our final answer should be -1. All right, example 4. Same thing we've been doing, except now we're going to do it in radians. Okay, so we're looking for sine of 16 pi over 3 as our first angle. So again, I want to sketch this first. Think about where we're located. Now, if you think about it, 2 pi is a full revolution. And if I change that to have a common denominator of 3, this would be 6 pi over 3. So I know 16 pi over 3 is much larger than that, so it's more than a full revolution. So just like we did with 360, we're going to have to subtract off those revolutions first so that we can figure out which quadrant we're even located in. So I'm going to take my 16 pi over 3. I'm going to subtract off a full revolution of 2 pi, which we just said is the same as 6 pi over 3. So we're going to do 16 pi over 3 minus 6 pi over 3. And if we do that, we get 10 pi over 3. Still bigger than 2 pi, right? Because that's still bigger than 6 pi over 3. And so we're going to subtract off another full revolution. So 10 pi over 3 minus another revolution. 10 pi over 3 minus 6 pi over 3. And that's 4 pi over 3. Now, 4 pi over 3 is smaller than 6 pi over 3. We're within one full revolution now, so we should be okay. So now the only question is, where is 4 pi over 3 actually located? Now, it's kind of up to you. Again, you could convert this back into degrees. Think about it that way. That's perfectly fine. I'm going to start to try to understand where these angles are located without necessarily needing to do that. Okay, so I know that one full revolution is 2 pi. That means that half of a revolution should be pi. And so 180 degrees, same thing as pi radians. Well, 4 over 3 is bigger than 1 pi, right? So 4 pi over 3 is bigger than 1 pi, so I know I'm beyond pi. This value down here is actually going to be 3 pi over 2 if I convert 270 degrees into radians. Well, 4 pi over 3 is actually smaller than that value. If you found a common denominator and compared them, you see they're actually 4 pi over 3 is smaller than that. So it's bigger than pi, it's smaller than 3 pi over 2, which means we're somewhere in that third quadrant. In this case, it is going to be slightly closer to 3 pi over 2. But don't stress yourself too much about whether you put that line in exactly the right place within the quadrant, because we're going to do our addition subtraction, right, to actually figure out what that value is. So it really doesn't matter. All right, so what we've shown here is we've gone 2 full revolutions, right? So we had to subtract off 2 pi twice. So we're going once, twice, and around to here. And so there's our angle. And so that is our 16 pi over 3. Again, to find our reference angle now, you're always going to draw your triangle back to the x-axis. And so our reference angle this time is that angle between the terminal side and the x-axis. Now, the easiest way to find that, I know that I went 4 pi over 3 beyond 2 full revolutions. And I know that my x-axis there is pi. And so if I take 4 pi over 3 and I subtract pi, excuse me, that should give us our reference angle. Now I need a common denominator, right? So 4 pi over 3 minus pi is just going to be 3 pi over 3. And if we subtract those, we should get pi over 3. So that tells us this time our reference angle, pi over 3. Now, once we have that reference angle, we're home free, right? We know how to find the sine of that. Then we just think about the quadrant. We make it positive or negative based off the quadrant, and we're good. So let's find the sine of pi over 3. Again, we're just going to go to our chart to help us find that. Sine of pi over 3 should be square root of 3 over 2. And now we want to know the sine of 16 pi over 3. And we just showed that 16 pi over 3 is in the third quadrant. In the third quadrant, only tangent and cotangent are positive, so sine has to be negative. So we get square root of 3 over 2. Again, same steps that we've been doing. I understand dealing with radians is probably going to be a little bit trickier to begin with, right? Just locating where those angles are. So if you need to for right now, go ahead and convert them to degrees just to figure out where the reference angles are. But then we can use that chart to find the sine. And then from there, just think about the quadrant to make it positive or negative. All right, and then part B here, we want to find the secant of negative pi over 4. And first step, let's sketch this. Now, pi over 4 is one that we've seen a lot, right? And so hopefully at this point, you're starting to recognize some of these. Pi over 4 is going to be 45 degrees. But because it's a negative, remember that tells us we're going in a clockwise instead of counterclockwise direction. So I'm basically going 45 degrees in this direction here. So this angle here, negative pi over 4 radians. Now, once we have that, again, we need to know our reference angle. Always draw your triangle back to the x-axis. Now, in this case, right, hopefully it's kind of obvious how big that angle is. Since we went negative pi over 4 to get there, we know that that angle itself is just pi over 4. And so what I want to find now is what is the secant of pi over 4. Well, the secant of pi over 4, if you look at your chart, is square root of 2. And so now we just have to think about which quadrant we're in. This right here is in quadrant 4. But cosine and secant in quadrant 4 are positive. And so in this case, we're just going to keep this a positive value. And so our final answer is still just positive square root of 2. All right, now we have what are called trigonometric identities, and we're going to look at these a lot more when we get to unit 7, but we're going to start with some of the basic ones. Now, some of these we've already even looked at, right? So the reciprocal identities, we've talked about those. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tangent, and so when we have to enter these into a calculator, that's how we're going to do it. 1 over sine, 1 over cosine, or 1 over tangent to get those reciprocal identities. Now, the new ones here, our tangent value, we can actually find by doing sine of theta over cosine of theta. So anytime you divide the sine value by the cosine value, that's going to be equal to the tangent value. And because tangent is just the reciprocal of tangent, cosine over sine should give us cotangent. And then down at the bottom, we have what are called Pythagorean identities. And these are going to be identities that are really important for us going forward. So sine squared plus cosine squared will always be equal to 1. And so if you know sine and you're looking for cosine, we can actually use this identity where we substitute the sine value in, we solve that equation for cosine, and that'll tell us what cosine is. Or vice versa, right? If you know cosine and you need to know sine, we can do the same thing. Then we have the same thing for tangent and secant. Tangent squared plus 1 is always going to be equal to secant squared. So if you know one of those trig values, we can easily substitute into this equation and find the other. And then finally, 1 plus cotangent squared is always going to be equal to cosecant squared. So again, using 1, we can help find the other. Now, for right now, I would say please start to memorize these. Hopefully the reciprocal ones we've been using a lot already, so you kind of have a good handle on those. Start to learn the tangent and cotangent ones here that deal with sine and cosine, because those will come up a lot. And then this first Pythagorean identity one, we will use over and over and over again. Okay, so please start to at least memorize those. As we get to test 3, you will actually have an identity sheet that will have all of these listed on it. So for your midterm exam, there will actually be an identity sheet here. So don't stress too much about memorizing them. You need to know when to use them, though. All right, so first thing we want to do here is express sine in terms of cosine. All right, so what we want to think about is, do we have an identity here that relates sine and cosine to each other? Okay, and the one that I recognize here is that we have a Pythagorean identity that tells us that sine squared of theta plus cosine squared of theta is always equal to 1. So if you're ever asked to write one trig function in terms of another, if you have an identity that just has those two in it, that's the one you want to go with. And now, since we're trying to get sine in terms of cosine, that means I want to solve this for sine, get sine by itself. Well, to do that, I need to move my cosine to the other side. So we're going to get sine squared theta is equal to 1 minus cosine squared theta. And then finally, to get sine by itself, I need to take the square root of both sides. So that's going to give us sine of theta is equal to the square root of 1 minus cosine squared theta. And don't forget that anytime you're solving an equation like this and you take a square root, you're always going to get a plus or minus in front of your square root. And the reason for that is if I were to work backwards now and square both sides, squaring a positive square root will give me 1 minus cosine squared, but also squaring a negative value becomes positive, and so I'm still going to get 1 minus cosine squared theta. So that's why we need the plus or minus there, because squaring either of those will give us the previous step that we started with. And that is our answer for this one. Now, if you're asked to do something like this in your WebAssign homework, there is no plus or minus in WebAssign. And so you would actually have to enter this as 2 separate answers. And WebAssign will tell you that. Usually it'll say put a comma between them. So you'd have to actually enter the positive square root of 1 minus cosine squared theta, comma, and then the negative square root of 1 minus cosine squared theta. All right, now, next piece is we want to express tangent theta in terms of sine. And this time they tell us that theta is in quadrant 2. So let's deal with the tangent in terms of sine first, then we'll talk about what to do with that quadrant 2 piece. Now, we do not have an identity that directly relates tangent and sine, right? So there aren't any identities that just have those two in it. So we're actually going to have to use a combination of a couple of identities to get this one. First one I'm going to start with, though, I do have one that says that tangent theta is equal to sine theta over cosine theta. So that gives me tangent in terms of sine and cosine. But again, what we want here is just in terms of sine, which means on the right-hand side of this equation, I only want sine values, no cosine values. So if I could get cosine in terms of sine, then I'd have exactly what I need, right? Because I could change that cosine to be in terms of sine. I'd only have sines on the right-hand side. Well, we just did one where we got sine in terms of cosine. We can do exactly the same identity to get cosine in terms of sine. So I'm going to take my sine squared plus cosine squared equals 1. But this time I need to replace that cosine, so I'm going to try to get cosine by itself. Well, that's going to give us cosine squared theta is equal to 1 minus sine squared theta. And again, we take our square root, which gives us cosine theta equals plus or minus the square root of 1 minus sine squared theta. Now, this time, they actually give us a key piece of information that's going to tell us whether we want the positive or the negative. So, if we're in quadrant 2, remember, we just found cosine. So we got to think about, well, is cosine in quadrant 2 going to be a positive value or is it going to be a negative value? Remember, in quadrant 2, sine and cosecant are going to be positive, meaning everything else is negative. So that tells us that cosine is going to be negative. So really, the cosine value that we care about, because we're in quadrant 2, is going to be negative square root of 1 minus sine squared theta. So solving the equation, we still get a plus or minus, but because they tell us the quadrant, that tells us specifically whether we want to take the plus or the minus. Now that we know what cosine is equal to, we can substitute that back in over here. So we have tangent theta is equal to sine theta over negative square root of 1 minus sine squared theta. At that point, we have tangent only in terms of sine, no other trig functions on the right-hand side, and we're done. All right, now the next one here, we're given that tangent theta is 2/3, and we know that theta is in quadrant 3, and we're asked to find cosine. All right, so first thing we want to do here is let's think about what the tangent of theta actually tells us and how we can actually relate that to cosine. So a couple of things we could do here. We could use one of our identities. We could also draw a triangle. Okay, and so I'm actually going to use triangles here. If you want to use identities, we can use actually what we just saw on the previous slide, get tangent in terms of cosine instead of sine, and then just substituting your tangent value to find cosine. That's one way to do it. In this case, though, I'm going to say, well, if I draw a right triangle, I put a theta in here. If you remember back in previous sections, we talked about what tangent tells us, right? We know what that ratio is. So in a right triangle, the tangent is the opposite side over the adjacent side. And so what I can do now is I can actually list out those sides in my triangle. So the opposite is going to be over here. That's 2. Adjacent should be down at the bottom next to my theta value. That's going to be 3. And now to find cosine, we need to know the hypotenuse, right? Because cosine is going to be adjacent over hypotenuse. And so I'm going to do 2 squared plus 3 squared equals c squared. Use your Pythagorean theorem. It's going to be 4 plus 9 equals c squared, which is 13. And then we just take the square root of that. And so we get square root of 13 up here. Now notice here, I'm not worried about the quadrant 3 piece yet, right? I'm only just drawing my triangle based off the tangent. I'm finding that missing side. Then we'll deal with the quadrant 3 piece at the end, because that's just going to tell us whether our cosine is positive or negative. All right, so now, based off of that triangle, if I'm looking at cosine of theta, I know cosine is going to be adjacent over hypotenuse. Here's my hypotenuse. Here's my adjacent. And so that's going to be 3 over square root of 13. But because we're in quadrant 3, we have to think about if that's going to be positive or negative. Well, in quadrant 3, tangent and cotangent are positive. Everything else is negative, so I know cosine has to be negative. All right. Now, number 7 says if secant is 2 and theta is in quadrant 4, we want to find the other 5 trig functions. Okay, so again, the way I'm going to do this is I'm going to sketch myself a triangle. I'll put my theta in there. And remember, secant is just the reciprocal of cosine. And so I'm going to write this as a fraction, 2 over 1. Cosine is adjacent over hypotenuse, which means that this should give us the hypotenuse over the adjacent. So 2 is my hypotenuse, 1 is my adjacent. So if I put those in my triangle down here, 2 is my hypotenuse, 1 is my adjacent. Now we just need to find that other leg, right? So we're going to do 1 squared plus b squared equals 2 squared. 1 squared is 1. 2 squared is 4. Subtract your 1, so we get b squared equals 3. Take the square root, b equals square root of 3. So that gives me the length of this side over here. Now, once we have our triangle, now we can find all of our trig ratios, right? So we have sine of theta. In this case, this is going to be my opposite side, my adjacent side, and my hypotenuse. Sine is opposite over hypotenuse, so that's going to be square root of 3 over 2. And for right now, I'm not worried about the positives and negatives, right? I'm only going through and finding these ratios. Then we'll come back and deal with the quadrant at the very end and put our positives and negatives in the right place. Cosine of theta should be adjacent over hypotenuse, which is going to be 1 over 2. And that makes sense because it's the reciprocal of secant, which we already knew is 2 over 1. Tangent should be opposite over adjacent. So square root of 3 over 1, or just square root of 3. And then we'll do our reciprocals. Cosecant should just be the reciprocal of sine. So that's 2 over square root of 3. Secant, we already knew, is 2. And cotangent is going to be 1 over square root of 3. So again, just use your triangle, find those trig ratios just based off the triangle first. Now, let's go back and deal with quadrant 4. So in quadrant 4, we know that cosine and secant are going to be positive. Everything else, though, needs to be negative, right? So only the cosine and secant stay positive. Everything else here gets a negative sign. All right, and then finally in this section, the area of a triangle. So we all know a formula to find the area of a triangle, 1/2 base times height. What this formula is useful for now is, well, what if you don't have this nice base and height that are perpendicular, that form a 90-degree angle? How could we still find the area of that triangle? So that's what this formula does for us. So it's going to be 1/2 a times b times the sine of theta, where theta is the angle that's between those two sides, A and B. So if you know two-sided triangle, and you know the angle between those two sides, we can actually find the area using this formula. Okay, so here we go. So we want to find the area of this triangle here. Again, our formula was area equals 1/2 A times B times the sine of theta. And theta has to be the angle between the two sides that are given. Well, for this one, we have area equals 1/2. We have two sides, 10 and 3. And we have the angle that's between them. So we're going to multiply that by sine of 120 degrees. Now, I do want to try to find this as an exact value, so I want to think about the sine of 120. 120, we think about that, it's going to be somewhere between 90 and 180. In this case, it's actually closer to 90. So here's my 120 degree angle. Draw your triangle back to the x-axis. Find your reference angle. So to find this reference angle, I'm going to do 180 minus 120, which is 60. And now I can actually find the sine of 60 degrees, because that's one of our special ones from our chart. And that should give us square root of 3 over 2. Now I just have to think about whether this is going to be positive or negative. In this case, 120 degrees, quadrant 2. Sine in quadrant 2 is still positive, so sine of 120 degrees, still going to be positive, square root of 3 over 2. So now we can actually plug all that in. So we have 1/2 times 10 times 3 times square root of 3 over 2. And now we just simplify. So in this case, we end up with 30 times 1/2 is 15. And so this is going to give us 15 square root of 3 over 2. And then as always, if you have units in your problem, always think about your units on your answer. We found an area. Our units here were in centimeters, so our area should be in centimeters squared. And then, of course, in WebAssign, if it asks you for an approximation to round to so many decimal places, then we could just put 15 square root of 3 over 2 into our calculator, get a decimal value, and then round that appropriately. All right, so that's everything in 6.3. Again, if you have any questions, please let me know. Come see me during student hours if you need to. Send me those questions on the homework as you have them, and I'll see you next time.